The title of our co-talk today with myself and Dr Alison Monaghan from BHS is Mime Water Heating from Research to Construction. But as you're about to find out, I'm probably going to present the construction first and then Alison the research last. So maybe a better title would have been Research and Construction or something like that. But here we go. So my name is Gareth Farr. I work at the Coal Authority. I'm the head of the Heat and Byproduct Innovation team. Our sort of main purpose there is to facilitate mine water heating schemes across the coalfield in Great Britain. And of course, the Coal Authority own and license access to British coalfields. So I'm trying to summarize an awful lot of stuff in one slide here, but on the right is a simplified image of perhaps what the extents of the coalfields look like across Great Britain. You probably don't need to be told that there's a good synergy there with some large urban areas and that they are quite extensive. Broadly, a lot of underground coal extraction and then also open cast. We've got records of 23,000 collieries that have all operated at some point or other across Great Britain. And it's estimated there's 25,000 million tons of coal that was extracted between 1853 and 2020. Those stats from Bayes, I believe. At the peak, the coal mining industry employed, well, probably over 1 million people, which is really quite a staggering thought. But now, as we're probably all aware, the majority of coal mines have now closed. But that means, of course, there's still millions of people living and working above coal mines. So I'm sorry, this is going to be a very Mickey Mouse slide, but for the non-geologists out in the sort of digital Zoom room, here's two broad types of coal mining. On top, we've got the room and pillar method, which is the earlier one, and then below that on the left, the longwall mining method. They both result in sort of different formations being left behind the longwalls, kind of designed to collapse, and the room and pillar may not collapse so much, but will collapse. And so that's kind of how coal was extracted, sort of very high level overview of that. And then on the right hand side, there's a little geological cross section, very simplified, of an underground coal mining enterprise. And you can see there it's dry and all the little coal carts are in there and the seams are being mined. However, during operation, a lot of coal mines were actively pumped to keep them dry of water. But when the coal mines closed and the pumps were turned off, what you have is annotated by this wonderful animation I made here in a PowerPoint, is flooding of the coal mines or mine water rebound. So what the kind of current state of play we have today is not all coal mines underground are flooded, but a lot will be flooded and will contain water within what are the anthropogenically enhanced features that have been left behind from the coal mining industry, i.e. shafts, galleries, and other features. All right. So perhaps bringing it more to the surface, which is where I know perhaps a lot of the audience are more happy and certainly more experienced, I'd imagine. So after the closure of the coal mines, dewatering stopped, and there has or still is in different areas mine water recovery as the mine water levels rebound up to where they perhaps would naturally have rested. And in certain places where geological or hydrogeological factors combine, the mine water will exit the underground environment and find its way often to the lowest hydrological point of a system and may very well exit there. And those, as you well know, are often rivers and river valleys and other features like that. So one of our principal jobs at the Coal Authority is to manage and treat a lot of this mine water that has resulted from nearly 2 centuries of coal mining. And we operate 76 mine water treatment schemes. They are not all coal mine treatment schemes, but most of them are. And we treat 122 million meters cubed of mine water per year. and that prevents 4,540 tons of iron solids and other nasties, I imagine, entering our watercourses. So we've had a big role to play in mitigating the impact of the historical effect, or the effects of historical coal mining. And these treatment schemes, one imagines, will continue to operate sometime into the future. So we've got what some people have termed an environmental liability, i.e. all this sort of water that can't really generally be used much. And so how can we turn that into a geoenergy asset? And hopefully that's what we will tell you about today. So first things first, the whole geothermal spectrum, if you like, and this figure is produced by BHS in a report by Kriner Abessa et al. And it's a really useful one because we quite often get asked about creating electricity for mine water and all these things, but this slide is really quite telling. So on the right hand side, we've got some of the deep geothermal schemes where you've got direct heat and electrical generation. And some of these are probably more akin to the United Downs and Eden project wells that are going on in Cornwall at the moment. And I think they're around 5 kilometers deep. There's a sort of funny argument between the two about who's got the deepest well, because one of them has the deepest well and the other has the longest well because it's slightly curved. So both fascinating schemes, and the visitor centre at the Eden project is well worth a visit because you can see the wellhead in place for their scheme. And if you move over to the left, we get into the much shallower ground source heating category there, really, where we've got mine water energy, and we've got closed loop borehole arrays and open loop borehole arrays that can go into mine workings, but also into potable aquifers or other rocks as well. So we're looking kind of really at the general cool end of things if we're thinking of geothermal as a broad spectrum. And mine waters, I think we expect, they'll be between sort of 10 and 20 degrees within a sensible distance from the surface, and we're looking at a couple of 100 meters for drilling, probably at max in most cases. Ooh. So how does a mine water heat system work? It's a very simplified image here, and hopefully the animation works. So we've got two seams ideally, but not necessarily. Up on the surface here, we've got little heat exchangers and heat pumps, which are these sort of grey items on the left. And then we've got a series of buildings, could be homes, could be anything else, connected via what is a district heat network. So the broad concept is that water is abstracted from a deeper seam or a seam, and it's put up through the heat exchanger, and that takes heat from the water. And then the slightly cooler water is returned to another mine seam. And then as the heat pump and heat exchangers do their magic, they can then transfer that heat to a clean loop of water, which takes it through the buildings and provides heat and hot water. So mine water heating schemes, are these new? No, is the answer. Globally, the first one we could find, 1979 in Wyoming in USA. They've also been around in Germany since the 80s. A big famous one in Europe is Herleen in the Netherlands. Fascinating scheme if you ever get to go and see it. And also Boredo in northern Spain has some district heat scale size schemes. So where are we in the UK? We didn't really pick up on this much early on. Scotland, there were two schemes that went in the late 90s, early noughties. They've operated for on and off 20 years, but they're both now closed, unfortunately. There's a couple of big schemes up in the northeast that really is the sort of hotbed, if you excuse the pun, for mine water heat at the moment, at least active schemes going in. So there's a commercial one at Lanchester Wines. There's work going on at Gateshead that I'll talk about, and there's currently drilling at Hebburn and Holborn for district heat schemes, and also work underway soon at Sunderland and Seaham. So it's quite busy in the northeast. Also plenty of interest in Scotland, including the BHS's UK Geo Energy Observatory, which Alison will tell us lots more about in the next phase of this talk. So the broad opportunities are fairly obvious, and this map on the right from Bayes has got a heat demand density in the sort of bright purpley to yellow colours, and the white outlines there are the outlines of the coalfields. And you can see there's a pretty good correlation between them in South Wales, the Midlands, north of England, northeastern Scotland. Less so down in the southeast, but then for the most part, they're devoid of coal mines for the most part. So we've got a good correlation with where people live and of course where they need heating in their homes and businesses. The other opportunity, or whether it's an opportunity or something we've actually got to do, is of course this is a secure source of heat. It's within the UK or within Great Britain, and it's something really that we hope could be a strategic importance given all that's going on in the world. And we've also got the transition to the green economy. You know, we're going to need heat pump engineers, and we're going to need scientists and all sorts of people to install, run, maintain these systems, and that could offer good jobs in the green economy going forward. But importantly, you know, these systems aren't blue sky science. They're using existing technology and approaches that have been proven at scale in other countries. And indeed, we hope to prove them at scale within our own country very soon. So I've got two little case studies for you, and these are divided into terminology that we use. So one is a bolt-on scheme. I'll explain what that is now. And the next one is a borehole scheme. So for those of you that have been involved in any sort of mine water treatment works in the past, this is a sort of little infographic of what the Dordon mine water heating scheme looks like in the northeast of England. So there's an existing shaft and the water is pumped out of that, treated, and in this case it's discharged to the sea, which is right next door. So the plan here is working with Durham County Council is to use this existing mine water treatment scheme where we're already pumping water from an existing shaft to provide heat to what will be a new housing development called Seaham Garden Village. And I had the pleasure of being up there the last month, and the sun was out, and you know, it was glorious. I would quite like to live in Seaham Garden Village. It's really fascinating location to be in. So that's kind of the setup of what we call a bolt-on scheme. In some ways, these are appealing because of course the infrastructure is there, the shaft is already there, the treatment scheme's there, and the coal authority already pumping the water to treat it. So a lot of the early capital spend, geological, hydrogeological risk, if you like, is minimized because the water's already being removed. So hopefully these things can provide attractive opportunities. I think we're getting, I think it's about 80 litres a second on average that comes out of this shaft, and the pump's at about 100 meters depth, as is the water table. It's maintained there to protect the magnesium limestone aquifer that lies above it. Water comes out pretty much constantly at about 20 degrees. So a good starting point there for amplifying it via a heat exchanger. If you wondered what it looks like, on the left is the coastline within a hop, skip and a jump from the old shaft. If you squint your eyes really carefully, you can see a sort of strange raised beach feature down there. That is actually just a huge amount of old coal and industrial waste. So really fascinating geology for anyone that's into the Anthropocene. The middle picture just shows the mine water being treated within the plant, and the picture on the left just shows the plant at large. So it's a large hangar basically with lots of treatment systems within it. So we hope this scheme will be on the cards soon. You know, just we're tying up the paperwork in effect, and hopefully we'll see the house builders starting in the near future. Oh, sorry, another slide. So here we go, an aerial view here. Here's Dordon mine water treatment scheme in the top right, and then here's the sort of series of homes that hope to be built and heated with a heat network. So 1,400 homes, 50-50 affordable to market, saving of 2,600 tons of CO2 per annum. So all really positive stuff should this one be realised. So case study 2 is the borehole scheme. This is one we've been working on in Gateshead with Gateshead Council. And you'd seen that info diagram before, so I won't play it. I won't play it again. The borehole scheme looks a bit like this. So the boreholes are going in, targeting different work seams. Two seams here, the high main and the Hutton one's at about 50 meters deep, which is the high main, and the Hutton is 150 meters deep. So we're not talking deep drilling here. We're abstracting from one, returning to the other. So these have been put on site on, in a good location here. So some sort of brownfield land. The image on the left is one of the abstraction wells. The pipework coming out is the pipework that was being used during a pumping test. The image in the middle shows what happened a few months later, where some concrete O-rings have gone round and the borehole is set down in the middle. And as you can see from the digger there, all the land is being reprofiled around here. And I believe there's going to be, on top of the Mime water heat boreholes, there's going to be a solar farm as well. And just off to the side is a heat plant where all the heat will be taken off the Mime water, and that heat will then go into a combined district heat network, because there's already a CHP heat network there, and this will add another 3 megawatts onto that scheme. So this should be the very first Mime water heat network scheme at this scale, at least, to be delivered in Great Britain. So exciting times, and in its very final stages of testing as we speak. So I'm sure all you surface water people out there will be more than knowledgeable on the various licenses and permits you need for any operations on the surface, and you'll be glad to know this is no different for hydrogeological operations below the surface. So for these schemes, we definitely need to speak to the environmental regulator. We need abstraction licenses and permits to discharge water back to the systems. You also need to speak to ourselves, that's the Coal Authority, for heat access agreements and all permissions to enter coal workings if you're indeed drilling new boreholes. There's always challenges with these things moving forward, and the thermal interaction of schemes is quite interesting because nobody actually owns heat in the subsurface, but I won't go into that one in detail here. But also how going forward, how we sustainably license multiple schemes in proximity to one another. Things I've floated around, do we need an approach that's similar to the source protection zones for groundwater supplies? What do we need to do to ensure these things can operate sustainably and without interacting in a negative way into the future? So just wrapping up really, the sort of summary and challenges. So good news, the Mime water heat resource aligns with significant urban areas in Great Britain. That's the first port of call. And we are just about to realise the first heat network from Mime water, although there's been smaller pilot schemes to prove concept and some larger industrial ones. And the technology has proven at scale abroad and will be here soon. So it's sort of technology that's ready to deploy in effect. But of course, with all of these sort of new approaches in a country, there's definitely R&D that we require to support this whole sector. We don't have a strong resource estimate for the amount of water, available water or heat in the coalfields. We haven't yet made opportunity maps that could help local authorities or developers dive deeper into the data sets to help them position potential schemes. There's the licensing challenges I mentioned about before that we're all working together on, but there'll be R&D required to see how schemes interact in one area when they're close to each other. And also for any regulators out there or consultants designing these schemes, we need good environmental baselines and an understanding of impacts, because without those, it's very hard to quantify changes above or below a baseline, or indeed what that may mean. And that could include, of course, groundwater quality, surface water quality, seismic monitoring, microbiological data, and so on. So I'm very pleased that my talk ends there, and I can pass over to Alison, who hopefully will answer some questions about what BHS are doing to address that.
Okay, thanks, Gareth. So I guess I'll just pass straight over, and I shall try and share my screen.
You'll just share your screen. I'll just read your introduction. So
Okay.
this Dr Alison Monaghan is a principal geologist at British Geological Survey. She leads the science delivery of the UK Geo Energy Observatory in Glasgow, including the mine water geothermal science and environmental baseline monitoring and open data sets.
Great, thanks
Alison.
very much, Rob. Thank you. Okay, so following swiftly on from what Gareth said, so really Gareth has shown that the mine water heat technology has proved that there are extensive potential resources in the UK, but he finished up by saying there are some sort of research and development challenges. So those are things like, how do we scale up these systems? There's some economic challenges. How do we make things economically viable? The sustainability angle Gareth talked on, if there was multiple schemes, and looking at the environmental impacts. And so what I'm going to talk about today is one aspect of research and innovation around that. As part of the solution, it's obviously a complicated picture, but clearly there's a need there for some research and innovation. So the thing I'm going to talk about is a thing called the UK Geo Energy Observatory, which the one I'm talking about is based in Glasgow. There's also one being developed in Cheshire, and the Geological Survey also looks after an urban observatory in Cardiff, and they all look at shallow geothermal technologies. But the Glasgow Observatory looks specifically at mine water thermal, which is why I'm talking about it today. And the purpose of these observatories is to really increase the evidence base, the real world data at scale that you can measure underground and at the surface through time. And they're places where different new techniques can be tried out, new sensors can be tested out, new technologies, and the detail of the processes that occur both under the ground and on the surface, and in the engineering infrastructure that is required to extract heat or store heat in the underground. So you can do lots of process-based work to really get to the bottom of those different aspects of the science. So overall, they aim to reduce risk, cost uncertainties. They're a place where things can be shown to work, and they're flexible and at scale because they don't supply heat to a user, which is means you can do research there that you wouldn't be able to do on a live site. So the site that I'm talking about is based in the east end of Glasgow. So this map shows us the city of Glasgow. It's got the River Clyde runs through Glasgow. And the Glasgow Observatory is based at two sites in the east end of the city of Glasgow. And on the next slide, this is an aerial photo of where the observatory is based. And the green and purple and yellow blobs, they are borehole locations. I'll talk about those more in a moment. But if I just first of all talk a bit about the urban area in which the observatory is based, you can see from this photograph that it's a mixture of kind of housing, industry, and it's an area of urban regeneration and has been for many years. Formerly, it was the site for many hundreds of years of different types of industrial activity. And because of that, the shallow land use has been very varied. So for example, on this site where we've got the bulk of the boreholes for the observatory, there's been both coal mining waste and landfill and an old waterworks, and all sorts of things really happened in the shallow subsurface. And then obviously under the ground, there are the coal mines. In this place, there are 7 mined coal seams, and the boreholes that are drilled here have penetrated into 3 of those coal seams. And fairly obviously from this diagram, this particular location is very close to the River Clyde. And so the Clyde is flowing in this direction around the Cunningar Loop and then down towards the sea. So from a groundwater surface water point of view, clearly there's a lot of interest there in terms of the interactions between the two. The other thing I would mention is that in some parts of Glasgow, so this area more towards Glasgow city centre, for example, there are known areas of land contamination, which is obviously a fairly common challenge in these types of urban environments. So it's a real world environment, it's an at scale environment. And the boreholes that have been drilled at the observatory go down at the Cunningar Loop to around 85 to 90 metres deep. And we've got a seismic monitoring borehole, which is, well, it's 199 metres deep, a bit further west. So the observatory itself, just to give you an idea of what the kind of concept is, or what it actually comprises, there are 12 of these boreholes, as I've just described, and there are 4 research compounds. This little picture shows a fenced compound, and they're places where people can go and do research and innovation, and they've got a lot of equipment in them. Obviously, the boreholes are there, and they've got a lot of sensors down the boreholes, and I'll come on to that again in a minute. Around the construction of this observatory has been a lot of stakeholder and public engagement, which has been very revealing and helpful in terms of learning people's reactions to these kinds of new technologies going in close to where they live. One thing I'll talk about in a little while is the environmental baseline. So a wide range of scientific environmental monitoring parameters have been looked at since before we started drilling the boreholes at this location to get the baseline in this complex urban environment before we start doing any geothermal activities. And one of the big things about the observatory is that the data is openly available that the Geological Survey collects, and that's available on a website as noted on this slide. And that's for many reasons, partly the scientific, but also from a public point of view, it means the data is there if people want to look at it. So just looking in a bit more detail at the underground. So this diagram is like a block diagram of the underground. These are the boreholes that have been drilled. These are the sort of central 9 boreholes that were on that previous sort of photograph. And they go down to about 85 to 90 meters to this deepest coal seam, the Glasgow main coal seam. And they also are screened across sections in the Glasgow upper coal seam. And then we've got some shallower boreholes that are environmental baseline monitoring boreholes, either in the superficial deposits, the glacial and post-glacial deposits, or in the bedrock above the mine workings. These boreholes were drilled in from 2018 to about 2020 and tested. And currently what we're doing is installing the geothermal infrastructure, so a heat center and a heat pump chiller and a pipe that's connecting all these different research compounds. And as I mentioned before, the boreholes have got a lot of sensors down them. So we can measure signals in the subsurface that are between the boreholes at different depths and different spacings and different scales to really understand in a huge amount of detail the variations in things like temperature, pressure, water level, and so on in the subsurface that are either naturally varying or vary when you start doing geothermal infrastructure. Your geothermal infrastructure starts working and you start taking out heat or you start putting heat back into the subsurface. So the next slide is just to illustrate what I mean a bit by those sensors. So this is a photograph of the borehole as it was being constructed. So this is a UPVC casing and a screen section with a gravel pack on, and down the side of the borehole are geoelectrical sensors, that's the red thing, and also a fiber optic cable that measures the temperature down the borehole. And on the right of this slide are 2 images that show those kinds of results. So these are the 2 boreholes that are next to each other, and this is a plot of the electrical resistivity between the 2 boreholes. And on the far right is a plot of the temperature down the borehole using the fiber optic cable over a month. So you can see there the temperature increases as you go down the borehole. And what these are both diagrams from when we were just measuring the baseline underground. But when we start abstracting water, taking out heat and re-injecting the water, clearly these kinds of techniques will enable us to look through time at what the responses are to things like temperature and flow within the subsurface. So really imaging the subsurface. And then I'm going to move on to water a little bit. So there's also sensors in there to measure the hydrogeology of the groundwater. So for example, here, this is a plot of the water level data over just over a year between 2020 and 2021 in 2 of the boreholes. This is actually available through an API. It's sensor data, time series data that BGS is starting to release in sort of digital form via a sensor API. So that's just about available online now. And really, a lot of hydrogeological data exists already and has been put out about the response of the boreholes to things like test pumping. So this is a graph showing test pumping of one of the boreholes in the Mime workings. This was the pump borehole. These were the responses in the same coal seam or just above that coal seam. And this was the response in a deeper coal seam. So we're learning a lot about the conceptual and the real hydrogeology under the ground. But really, one thing I just wanted to talk about a little bit today, given your interests, was about the subsurface to surface interactions, because clearly we've got the River Clyde very close. And so understanding what's happening with these boreholes, this is a cross-section of our underground geology, but understanding what's happening with these compared to the River Clyde would be about up here on our diagram. It'd be just above the ground, above 0 meters up here. But understanding if there are pathways from the subsurface, from the coal mines or the bedrock overlying the coal mines or the superficial deposits to the River Clyde is obviously really important once we start pumping. And also knowing that some of the ground has got a real mixture of legacy of land uses in it. So understanding the subsurface to surface pathways is an important part of what we're trying to do. And clearly we've got the boreholes at different depths to start understanding that. And we can already see, for example, that the groundwater head is upward. The water levels are much higher in the deeper boreholes. So again, we're starting to learn a little bit about that. And so what I thought I'd do is just show some of the surface water data in a moment. This slide here is just a summary of the kinds of baseline data that I mentioned before that we've been collecting. And again, really just a cartoon on this left-hand side of the picture to show really what we're trying to do here is look at the things that are happening underground. In this case, we might be heating the groundwater in the borehole, but there's a range of surface infrastructure where people are measuring the responses on the subsurface. Oh, sorry, on the surface. And some pictures of my colleagues doing that on the right-hand side. Okay, so just a couple of slides on the surface water that's been collected so far. So this map shows the observatory sites in the red, and the blue are places where surface water sampling has been ongoing. The data set that I'm showing here was 14 months worth of data collected monthly between 2019 and 2020, and we now have another about 6 or 7 months of data that will shortly be released from subsequent years. And really this is the baseline sort of data before the geothermal infrastructure was in place. But really the surface water sampling sites were chosen both to be upstream and downstream of the Geoenergy Observatory and also on one of the tributaries. There aren't many places for the smaller streams because most of them are culverted. So here are my colleagues doing some surface water sampling on the River Clyde, and they collected a wide range of sample bottles for different types of analysis, both inorganic, organic, isotopes, and so on, as well as field parameters. And here are some of the graphs from those results. So just explaining what the things are on these graphs. The green line here are the results from the tributary, the Tollcross Burn, so the smaller stream. All these other results that group together are from the River Clyde, and the blue bars here are rainfall data from SEPA. So what's immediately obvious, this is the SEC, the electrical conductivity readings. It's really obvious, you can see that the smaller stream is much more mineralized than the River Clyde, and the River Clyde groups together. And you can see similar trends between the two water bodies in this plot, which is iron content. There are some variations within the River Clyde. There's some higher values, for example, at one part of the River Clyde where the flow wasn't so great and there was some bank seepage. But you can see there are seasonal variations essentially within this data set, as you would expect from the surface water body. But this gives us a really good indication of how things are changing before we start doing any geothermal activities. We've also got sets of data where we've been looking at, has there been any impact of the drilling that we've done? So this is a plot of the sulfur because mine waters are probably richer in sulfur, sulfate, sorry, than other waters. But really the conclusion of my specialist colleagues who've done this work was that throughout our drilling and also some discharges we did into the River Clyde, there wasn't really any impact of discharging that surface water or drilling into the groundwater on the kinds of sort of determinants that we would expect if mine water was causing a problem on the surface water body. So from our point of view, that was a positive result. And this data is available online if you're interested to have a look at it. So I'll just pause there and just finish off what I'm going to say. So just stepping back a bit again from the surface water data, essentially what the observatory in Glasgow is about is some infrastructure which enables us to collect a load of really high quality data looking at the subsurface in 4 dimensions really, in space and time, and a place to go and do different types of measurement. And what that means is we learn a bit about the mine water heat resource, how big it is and how sustainable it might be, but also about the environmental impacts, for example, if there are any environmental impacts on the surface water. And together they will help go out to these sort of wider aspects of implementing mine water heat, where things like social acceptance, if people are concerned about whether there are environmental impacts, and the regulatory and licensing environment that Gareth talked about. So last slide, just to finish. Hopefully both Gareth and I have shown that mines are a place where you can both extract. We haven't talked so much about storing heat, but that's also a possibility. So extracting and storing heat in using flooded abandoned coal mines could be, or it can be, a sustainable way of heating homes and businesses in our towns and cities. And really what we're kind of working on now is the need to move at pace with the drivers of carbon reduction emissions, of fuel poverty, and now also of energy security. So we need research and innovation to underpin some of that, as well as the construction of active schemes. So I've talked a little bit about the Glasgow Observatory, which is a unique publicly funded infrastructure to support this development, to look at both the resources, the things like heat transfer and the energy efficiency, to look at any wider impacts and a place to test new technologies. And hopefully together those kind of things will be the kinds of technologies we need to decarbonise our heating towards net zero targets. So I should stop there, thank you.